Hello world, it's Craig. I finished repairing my Prompt 48 and I'm putting things back together. There were three problems going on with this system. The first that was certainly causing this to not work was a bad 8216 bus transceiver. This is a 4-bit transceiver that Intel put out. It was controlling the low nibble of the bus on board. It was bad, so the processor was just getting corrupt data off of that bus. The second thing that may have been a problem was we have this 8224 clock generator. Now the 8224 was made for the 8080, but here they're just using this 19 megahertz crystal here to generate a 19 megahertz and a couple of other frequencies that go around the board to do various latching and make a few state machines and that sort of thing. Those were both replaced and the board started working when I fixed those two. The third was a power supply issue, and it wasn't severe enough to be causing problems on this board, but it's going to be the subject of this video because I think it's much more general interest. If people are interested, we can come back and we can look at the details of how this board works, how the prompt works in general, and all the things that it can do, but right now we're only going to look at the power supply. The power supply uses an LM723 voltage regulator for the output control. Now, they also are using a feature of the LM723, which is has overload protection in current foldback. And they have another 723 that they're using as a crowbar for overvoltage protection. So I think that combination of being a real power supply with real currents, this is 6 amp power supply, and it's not some data sheet that has 100 milliamp output. It has current foldback, so using that feature of the 723, and then tacking on this crowbar kind of makes this an interesting real-world type of application. Now the 723 goes back to the late 60s, and they've been used for decades. If you're working on vintage equipment, you're bound to find them in some of your linear power supplies. I think Fairchild introduced it in 68. It's in their 69 catalog, and it came out about the same time. I think the 723 came out just shortly after the 741 op-amp. And the 741, of course, was the world standard op-amp. We all learned on the 741. Now, when I'm diagnosing a system like this, the first thing I do, and what I did in this case, is I start testing the power supply. And I put loads on the power supply, and I check to make sure that it's working okay. In this one, I found that it wasn't. It was starting to droop when the load was applied to the 5 volts. I really recommend getting a handful of these little adjustable loads. I got these several years ago off eBay. I think they were $10 or $15 then. But they are worth every penny of that if you are doing power supply testing. They have a little barrel connector here. I run these off of little brick power supplies or wall warts. Because of that, they're all isolated from each other and from ground. So any number of these can be used simultaneously on either referenced or completely floating power supplies. These 60 watt ones can sync up to 10 amps, but they can be put in parallel when you have more need for more current than that. Now the prompt, there's 2 schematic pages for power supplies, and my prompt is using the second version. This was a commercial version that they offloaded. They had somebody make these power supplies for them. Zentech made it for them. This was also used in the prompt 80. Which is a bit interesting. I always thought the 48 was made first, but the drawings just reference this as a prompt 80. And I haven't actually looked at my prompt 80 to see what power supply is in there. Overall, pretty traditional configuration. Out here we've got a fuse input. We can tap depending on what voltage input we have. A transformer, and then we just have the outputs here. This top output is the 26 volts. This is the bulk. This is the 5 volt output here in the center. Then down here at the bottom we have plus and minus 12. They're little minus 5, they're just taken off of the minus 12. All of these low current ones, the 26 volt, the minus 5, and the minus 12 are all just using 3-terminal regulators. 79, what's it? The 79, the 78, like the 7805, the 7905, 7912, those were actually relatively new when this came out, in 75. Those came out after the 723. So by the time this came out, this chip was almost a decade old, and the 3-terminal regulators were the newbies. Now the 723 itself is just a voltage regulator, but it's can be configured in a number of different ways compared to just a 3-terminal regulator like the 7905. It was extremely popular easy to use. It was made by everybody. All the manufacturers made these things. They're still readily available for 50 cents a piece. You can find data sheets from all the usual suspects. So let's look at the 5 volt on this power supply. There's these two 723s. First one is operating as the primary output controller. And the second one is a crowbar circuit to clamp the output voltage in case something upstream craps out and we don't want this to get high enough that it can start damaging chips on the prompt. So we want this crowbar to stop the output from going above whatever its set point is. So everything on this side is for the main power supply. All of this over here is for the crowbar. When working with the 723, we just need to think of it as an application-specific op-amp. Like an op-amp, if we draw our typical op-amp, we're going to have a non-inverting input and we're going to have an inverting input. And then we have our output. To summarize how an op-amp works in one sentence, if the plus input is higher than the minus input, then the output is going to swing towards the positive rail. If the minus input is higher than the plus input, then the output is going to swing towards the minus rail. So if we look at the equivalent circuit for this is the Fairchild catalog in 71, I think, or something like that. If we look at the equivalent circuit, we can see that this little triangle in here is the op-amp. This is the air amplifier. So we have a non-inverting input and an inverting input. But there's some additional components around here that make this a part of the voltage regulator. So the first thing that we notice is this air amplifier feeds this pass transistor out here. And this pass transistor is what drives the output with the current. This can put out about 150 milliamps. Now also connected to this output is this Zener diode here and a terminal called VZ. This is about a 6 volt Zener diode, and so that means that if this is forward biased, so VZ is higher than V out, the most that VZ can be is about 0.6 of a volt higher than V out when it's forward biased, or it can be about 6 volts less than V out if this is reverse biased. Now this is normally used for negative power supplies, but we'll see that they also used this in the crowbar circuit just to drop 6 volts somewhere. Also connected to the output of this air amplifier is this current limiter transistor. And the emitter and the base of that transistor just come out to terminals on the chip. Now, normally this series pass transistor is being driven by the air amplifier essentially. So this air amplifier is driving this series pass transistor. If this current limiter turns on, we can see that it will sink some of the current that is normally going to the series pass transistor, and what will happen is that series pass transistor will start to turn off. The more we turn on this transistor for the current limit, the more the series pass transistor will turn off or pass less, and that essentially starts shutting down the power supply. And finally, over here on the left-hand side, we can see there's a voltage reference. So this is another output pin. It's got a little buried Zener diode in here, little current source. That voltage reference on this chip is going to be about 7 volts. It may vary a bit, but it needs to be rock steady at whatever it is. And as it turns out, that was the problem with this chip in my power supply, was that voltage reference was wandering about. You can see there are different power pins. Here's a voltage pin that actually controls this part of it, the reference and the air amplifier. And then there's another power input pin over here. So this would be your main output current. So you could have those connected to different supplies if you needed to, maybe even different voltages. Okay, so let's look at that on the power supply for the prompt. Pin 6 is the voltage reference. So that's the 7 volts that's coming out as the voltage reference. Pin 4 is the inverting input. Pin 5 is the non-inverting input. So this is the plus input. This is the minus input. And pin 10, going into the base of this Darlington pair up here, is the output. The two supply pins are pin 11 and 12, and they're just connected together to the same power supply here. There is also this capacitor down here I didn't mention, but if we look at the circuit, there's a frequency compensation that's also tapped here between the air amplifier and the pass transistor. Here they've got a little 1,000 puff capacitor. From that compensation comes back into the negative input. Now if we look at this configuration, we can see that that is very similar to a figure in the data sheet. This is the foldback current limiting. We have on the output, we go through a sense resistor. At the beginning of that sense resistor, we have a little voltage dividers here down to ground, and that is what comes back into the current limit. Okay, so these circuits are very similar, and of course the big obvious difference is that this one has this big Darlington pair transistor in here driving the current, where this one doesn't. You know, this 723 can only drive 150 milliamps. This is a 6 amp output power supply, so that Darlington is what's, you know, making up the difference in that current drive. This current foldback or foldback current limiting power supply, let's talk about what that means. By current foldback, we mean the power supply will decrease the overall power output to protect that transistor. So let's look at, you know, just a couple of examples of current limiting power supplies. You know, if we have our voltage here and our current here, we want to output a fixed voltage, but at some point this power supply is going to be overloaded, and so that's going to be, you know, some critical current out here. And when we hit that current, we don't want this to just keep going. We want to shut this off somehow. And if we just use a current limiting power supply, that's going to roll off and it's going to come down here. It's going to have this little knee or roll off. It's going to come down, and basically it has switched from constant voltage over into constant current, or I guess more accurately, current limited. So it's going to be at this fixed current that's our limit. But the thing is, if we look at the power that's being dissipated in the pass transistor, whether it's the internal pass transistor in, let's actually look at the right circuit. This is one for just a regular voltage limit, either the pass transistor that's internally, or if we have a big pass transistor outside. That transistor, this isn't the minimum power that transistor is having to dissipate, because right here we're at some voltage and some current, but as we go down this curve, the voltage is getting bigger. The voltage drop across that transistor is getting more and more, because at some point down here at short circuit, it's dropping the entire voltage between the input from the power supply to its output. So let's pretend that this were in current limiting mode. If we're to the point where this is at this very bottom, this current limit, the entire voltage drop from the collector to the emitter is being dropped across that, or I guess the entire voltage drop from this transformer to the output is being dropped across that collector emitter. So we have the full current, we have the full voltage drop, and so we're just dissipating more and more power the further down that curve we go. Now ultimately, at short circuit, the pass transistor is presumably under its maximum, and it's relying on either a fuse to blow somewhere upstream to end the misery, or the magic smoke is going to come out of that transistor, or it's within specs and it's just dissipating that all as heat. But now let's look at another scenario, which is a current foldback. Let me get another color pen. So here in current foldback, let's say we've got our voltage and our current again. So now what we want to do is we're going to come out here with our constant voltage just like we did. We're going to get to some threshold where we just can't stand this anymore. But rather than come straight down, what we're going to do when we have current foldback is we're going to fold this back to a lower value in our, we're going to output a lower value in our voltage so that this load is going to take less current. And we can adjust that. You know, we can fold it back harder and harder. We will get to a point down here, and we will call this is going to be our short circuit current down here. So this is our foldback point. This is our knee, and this is our short circuit, or we might call this our holding current down here at the bottom. So this is a foldback power supply, and this is just a current limiting power supply. Once we've done this, we folded back, we are reducing the amount of current going through that transistor. And so as we reduce that current, this transistor, this pass transistor, we're reducing the amount of power that it has to dissipate. Of course, it still has a decent voltage drop across it, but we're reducing the current, so we're reducing how much power that has to dissipate. And the idea is that once we get down here to this holding current, we just leave it down there as long as we're in the overcurrent situation. And this transistor then, it's in a safe space that it can dissipate all of that heat and not have a problem. The knee going from constant voltage into this foldback, it's smooth, but it's not gradual, and the power supply may completely transition in milliseconds. So it's slow enough that it shouldn't cause problems if we have an inductive load out here, but it's not something that you're going to watch on a voltmeter in case that you're hoping for. Now if we go to the data sheet, we can see they've just got equations for this. So if we're referencing this foldback current limiting circuit, here's our equations that give us both the knee, the current for the knee, and the current for the short circuit. But as we will see in a bit, for our power supply, these equations aren't quite correct, and so they have to be adjusted a bit. Part of this shows the capability of the 723 because this voltage is just coming right off of the transformer for that 12 volts. So that's a pretty rough ride because this power input is just riding on top of that ripple of all that's coming out of that 12 volt transformer. Pin 6 is the 7 volt reference output, and that has a potentiometer across it, R12, which then has an additional little resistor down here, R13, to set the minimum. And so this gives us our set point into pin 5, and that's the non-inverting input. There's trim pots on this side of the board back here for adjusting the 26, the 5, and the 12 volts. So that trim pot right there for the 5 volts is this little pot right here. Pin 4 is our inverting input, and that is directly connected to pin 3, but that is our output. So that's our actual output on the pin of the power supply coming back into the inverting input. So we have the set point on the non-inverting input, the actual voltage on the inverting input. If we put our brain into op-amp mode, if the output voltage is below the set point, then the output on pin 10 will move towards the positive rail and bring the transistor Q3 further into conduction and provide more current to the output and raise the output voltage. That output voltage will come up until it raises the voltage on pin 4, and it'll continue to increase that output until pin 4 and pin 5 are the same, and that error amplifier goes to 0, and then it's stable again. Now conversely, if the actual voltage here is above the set point, the output on pin 10 will move towards the negative rail or ground, reducing the current Q3 is passing and causing the output voltage to drop down. Pin 4 and pin 5 will be the same, and so then the mirror amplifier will go back to 0 and it'll go back to being stable again. So you can see that we just have negative feedback here like a normal op-amp circuit that will keep this so that the set point and the output are the same. So it'll change the output to match whatever the set point is. Okay, as a basic power supply controller, I think that's straightforward enough. So let's look some more at this current limiting capability or aspect given to this voltage regulator through that extra input, through the current limiting input. If we look at the equivalent circuit for the 723, there's these two additional pins that we notice. There's the current limit and the current sense. The current limit is the base of Q16 and the current sense is the emitter of Q16. And on our diagram, those are pins 2 and 3. So the base is the one that's between this little voltage divider, and pin 3 is the current sense, and that's just tied to pin 4, which is the inverting input. Now under normal operation, the current passing through this inverting output transistor Q12 is controlling the base of this output Q14. So you can see Q14 and Q15, they're just forming a Darlington pair. They're being fed by this resistor and Q8, I think it is. But Q12 is siphoning off current from that to close this transistor down and shut down the output. But now we have Q16, which is in parallel with that, so it also can close down the output by siphoning current away from Q14, which is the output of this. So if the current limit goes high enough with respect to its emitter, the current sense, then Q16 will go into conduction, and let's say that happens at 0.6 of a volt. As it begins to conduct, it will divert current away from Q14. Q14 will conduct less, and this output starts to shut down. At this point, Q12 is immaterial because Q16 can divert enough current to completely drop this voltage down, and so all of this output completely shuts down. So Q16 can just shut down this output by itself. For a basic current limit, where we just want to do this kind of thing, we just want the voltage to come along, and then when it gets to a certain set point, we want it to go into current mode and just drop. We can use this circuit right here where all we have to do is put in a sense resistor in the output. As current passes through the load, there'll be an IR drop across this resistor. Let's say it's a 5 ohm resistor and 100 milliamps are passing. So the voltage drop is going to be 500 millivolts. And that's being applied to the base of this Q16. That 500 millivolts isn't enough to turn Q16 on, but let's say that we go up to 120 milliamps. So somewhere between 120 and maybe 130 milliamps, we're getting to the point where we have reached the turn on voltage of that base, and that Q16 starts to conduct. And as it starts to conduct, and it's going to throttle this output, and it's going to hold that output at whatever it takes in order to keep that 0.6 or 0.65 or whatever voltage it takes to keep this guy into conduction. It's going to hold that and throttle that to maintain that 0.6 volts across that. And that's how we basically maintain this constant current mode. Sure, we're putting away a lot of heat out of that transistor or whatever's driving this, but as long as that transistor can hold it, then this is going to be stable. Then as that current goes back down, this voltage drop, the IR drop across this, falls below whatever the voltage is required to keep this into conduction. Then it just comes out of constant current mode and goes back into voltage mode. So it just follows this back the same way, the same path that it came. And that's, all presuming that this past transistor, either this one or an external one, survived that being short-circuited. You can see if we look at the foldback current one compared to the constant current one, the only difference is this has these two resistors here in the divider, R3 and R4, where this constant current one doesn't have those two resistors. So you really get the current foldback for free on this when you're using it this LM723. But it's not just a matter of choosing one resistor like we could have when we were doing this constant voltage, because now we have to hit, or this constant current, we have to hit 2 points. We have to hit exactly when we want this need to occur, and then we have to decide where we want this to cross this zero voltage or this short circuit point. So we have to hit 2 points when we're calculating all of these resistors. In this circuit, there's a term in here, it's called sense, is basically the on voltage, the turn on voltage of that Q16. And we can find it, it's in a chart up here. It's right here. This is the current limiting characteristics as a function of junction temperature. So we have got the voltage over here. This is 0.7, so we can see that at 0, this is about 0.7. So that transistor turns on at about 0.7. By the time we get to room temperature, we are up to maybe 0.65 volts, or down to 0.65 volts. And then it goes on up here, and it's fallen down to half a volt. By the time this gets up, it's a real finger burner up here, very temperature dependent. And we'll run that to our advantage in a little bit. So if we use their circuit for the current feedback, the foldback current limiting, we use their equations, we would get, using their values, a knee of about 112 milliamps. So for that circuit right there, this knee will occur at about 112 milliamps. And to get that to happen, all we had to do was make sure that this voltage input to CL hits whatever we saw on that graph, the 0.6 or 0.65, when this output gets to the 112 milliamps. And that will start conducting, and it will hit our knee. To get this bottom part, what we do is we set our output voltage to 0, and we see what current it takes in order to maintain that 0.65 volts, or whatever our set point is, 0.6, 0.65, whatever's off our graph. Because we have to maintain that in order to keep this down here in the foldback. We can't let go of that base, because if we did, this would just come out of foldback and it would immediately go back to the overcurrent situation that it was in before we put it into foldback. So that's why this is called the holding current, because it's the current that it takes to hold that transistor Q16 into conduction. Look at their equations and we take their values again, we will find that this holding current for their example is like 32 milliamps. That's what it takes to still keep the 0.65 volts across that transistor to make sure that this stays in foldback. As that device warms up, and we saw from those graphs earlier, as it warms up, that voltage is going to decay, it's going to drop. That's to our favor. We don't have to worry about it falling out of foldback as this heats up, because as it heats up, that required voltage to keep it in foldback drops further and further. And when I'll show you a test in this later, I actually just set it at 8 amps, which is the foldback current for this. And I just waited. Eventually, it got warm enough that it fell below that voltage and went into foldback. Now, a key thing for me is when we hit this knee, how do we know that this is going to go from the knee to our zero voltage and that there isn't some stable point in between? How do we know in this circuit, just looking at this circuit, as the output starts to drop off, that this current or this voltage into the current limiting transistor base is always going to be above the 0.65, and it isn't, somehow through some quirk of fate, it's not going to drop off faster, or it's not going to allow this to just recover. Because if it just recovered, then we would really just have negative feedback, and it would go back up to where it was before, and then it would come back down, go back up, come back down. I was having a difficult time convincing myself that I understood why there was not, or there could not be, any stable points between these two, that it had to go down here to the zero current as soon as it passed the knee. Hitting the knee, the calculation is straightforward and it makes perfect sense. Hitting the short circuit, straightforward, makes perfect sense. But I couldn't convince myself that there was not like a local minimum or something between these that would allow it to get stuck somewhere between these two. And I struggled with that, and I asked a few people who were better at this sort of thing than me, and collectively we didn't come up with a fully intuitive answer. But then, of course, YouTube and Google, they know everything that you're thinking, and YouTube offered up a video, and that presenter addressed this specific point. What he did, and I'll put a link to that video down in the description, but what he did was he said, let's redraw this circuit. It's hard to see what's going on in this circuit. Let's redraw this as a simple bridge. We have coming up here the emitter, and that's this line right here. It's coming out of the emitter of the Darlington pair. On the left-hand side, we're going to draw our two attenuating resistors. So this is R3, R4. That's this resistor and that resistor. Right now, let's ignore this R16 because that's different than their circuit diagram. Their circuit diagram, this would be R3, that would be R4. Okay, and these guys just go down to ground. Also in the middle of that is our current limiting transistor. Okay, so this is drawing current out of the, what was it? It was Q14 or something. So this is the one that's drawing current, diverting current away from our output stage. So it's turning off the output stage of the LM723. So that's coming into this current limiting transistor. This guy comes out here, and that is essentially connected to V out, right? So this is our base is connected between these two voltage dividers, and pin 3, which is this pin down here, that just comes to our V out. Now let's draw the rest of this bridge. We come in here and we've got our sense resistor. So this is our resistor of the sense. And then down here we have our load. So this is our load. This is basically the same, well, it's exactly the same circuit as this, but it's just drawn, the components are just in a different order. This point right here is VB. This is our voltage drop, V from the base to the emitter. And this is the voltage drop that has to be above the 0.6 or 0.65 or whatever's on that chart in order to turn this guy on and keep him on. So going back to the original problem is, how do we know that this voltage right here is always going to be above that 0.6 even as this starts to go down? Why is this shutting down? This is shutting down because this load resistance is decreasing to some threshold. That's causing our current to go up. As our current goes up, this system wants to start dropping V out. Okay, and that's the whole function of this is, this circuit is going to start dropping V out. So V out is actually our controlled parameter here. The whole purpose is to drop V out. We can look, if we look at this as a bridge, there's really no question that at any time, if there's any change in V out, it's attenuated by these three resistors, by the sense resistor R3 and R4. Any change in V out will always be faster than any change in VB because it's attenuated by the time it gets back to VB. So V out will always change faster than VB. So if we first get to this 0.65 and we're on our way down with V out, this is going to be 0.65, but VB is going to be changing slower than V out, and so it's always going to be above the 0.65. So there can be no hidden points where this is stable between the knee and the zero current. Because once it hits the knee and V output begins to decrease, VB will decrease slower than V out, so the voltage across this junction can only increase. And that's how we know that this is stable all the way down. But of course, we can't go all the way down to zero because we have to keep VB high enough to keep this current limiting transistor into conduction. And that's why we have, those minimums that we saw on our power supply, or our minimum current. For me, drawing it as that bridge, it was a stroke of genius, and it completely resolved, my question, or maybe I just had a lack of understanding of why it has to complete this foldback once it starts. And I guess for years I just looked at the data sheet and said, yeah, okay, sure, whatever. I'll take your word for it. Now to get this out of current foldback, all we have to do is reduce the actual current below our set point current. Then what happens is this error amplifier is going to flip, so it will immediately jump from wherever point it was right here back up to maintain or back into constant voltage mode. So all we got to do is get the actual current below the set point and it'll immediately pop back into normal operation. If we look at their circuit compared to what we've actually got going on here, when we put their numbers in, this was 112 milliamp for the knee. What we want is 6 volts for our knee, or I'm sorry, 6 amps for the normal output and 8 amps for the knee. They are using a 30 ohm resistor for the sense. We can see right away that we can't use a 30 ohm resistor. In this power supply passing 6 amps across a 30 ohm resistor, we're already talking about it. There's a kilowatt. So that's a non-starter. We have to have a much more reasonable sense resistor, and this is down at 1/10 of an ohm. If we then put 1/10 of an ohm into the equations for this circuit, so if we just change from that 30 down to 1/10 of an ohm, what we'll find out is that if we use an 8 amp knee, we can calculate out and find the ratio of R3 to R4 without actually picking either one. We can find that ratio, and we would find that R3 needs to be 2% of R4. We then take that and we plug it into the short circuit equation. That tells us that if we want our knee to be 8 amps, our zero voltage current limit is going to be 6.6 amps. And our whole output is only 6 amps. So if we have a knee that we think is reasonable at 8 amps, we're down here at 6.6 amps, and we're still abusing this transistor. And we can say, well, okay, instead of 8 amps for the knee, let's take it back down to 7 amps or 6.5 amps, or we can get closer and closer to this value right here, but we're only going to zero in at 6.5 amps for the short circuit current, because it's basically just the dominant factor turns out to be that 0.1 divided into the 0.65 of that current limit. We're only going to approach that 6.5 amps. So how did Zentech address this problem? Well, that's what this other R16 resistor does. They added this R16, which gives us one more variable to refine the knee and the holding current points. So now it gives us one more variable to adjust those two values. And that's because R16 is going to bring in additional current from this base of Q3, or the output of 723. It's bringing additional current into the current limiting base. We know that no matter how low this goes on the emitter, the base is always going to be at least 2 junction drops above that. So this is going to be at least 1.2 volts above that. And by the time we get up to decent currents, this could be 2 volts or 2.5 volts or 3 volts above that emitter. Instead of only having this very low voltage to play with, we now have something that's going to be 1.5 volts or 1.2 volts at least higher to feed into this current limiting base. So we can calculate that, we can create that equation, and we can figure out what the voltage contribution to the current contribution is from this R16. And if we do that equation, it turns out that the voltage drop across R16 is just equal to our base emitter junction minus the voltage sense, or the voltage that it takes to turn that on, minus the voltage drop across this sense resistor up here. So I took, for that equation, I took 3 volts as being the base emitter voltage when this is passing at the knee. So at 8 amps, I said, okay, well, let's say that this is 3 volts. I put 0.65 as the turn on for this current limiting transistor. 8 amp knee, so that gave me 3 plus 0.65 minus 0.8, which would be the drop across that at 8 amps. And that turned out to be 2.85 volts. Divided that by 470 ohms, which was the size of that resistor, and that tells me that this part of the circuit is contributing about 6 milliamps. 8 amps, so we presume that this has a beta of at least 100, so that's driving 80 milliamps into the base. The extra, what was it? It was the extra 6 milliamps isn't going to be a problem with that. So those are appropriate numbers for that circuit. Then if we use those values for the foldback and look at this zero, or the short circuit current, I took VBE to be about 2 volts across that. That gave us a voltage drop across R16 of 2 1/3 volts, gave us about 5 milliamps there. So once we figured all that out, now we could go back and we could look at the rest of the circuit. We find that R15, when we are at the knee, it's about 0.15 volts. And then when we are down here at short circuit, this is minus 0.35 volts. So actually this base output junction is feeding not only that current limiting transistor, but it's feeding backwards through this R15, and going out into the load. So all those numbers were at least self-consistent, and they looked like they were working okay. I wasn't planning on doing that equation, but it was worth working that out. And then I went and I actually plugged in the actual numbers. I took the knee at 8 amps. I measured this, and it did indeed cross. Its zero voltage was at 3 amps. I was off a little bit by the current going through this resistor, by like 25% on that. So here is a oscilloscope trace of a current foldback for this power supply. The top trace is the base voltage into the Darlington pair. Next down, the blue trace is the emitter voltage. The third trace down is the voltage going into the base of the current limiter. And the bottom trace is the voltage output. And so you can see that that's running right at the 5 volts on the way in. You can see there's a slight dip and then a recovery right before it folds back. You don't see the current limit base increase in voltage. So as this was going on, it wasn't increasing the voltage. You would think that, okay, to trip this foldback, base voltage of that current limiter needed to go up. But what was actually happening was I set this, as I mentioned earlier, I set it at 8 amps, and then I just waited. And what was happening was this was internally heating, and that trip voltage, or the conduction voltage of that Q16 was dropping, and it got to the point here where it dropped enough that then everything just rolled off. Then it drops down to about 1 volt. The emitter is 1.3 volts, so that means we have a 0.3 volt drop across R14, which is our sense resistor, which is 3 amps. Okay, that's enough about the voltage regulator. Look at this crowbar. What we've got is this other LM723. Here, they're simply using it as a comparator with a precision voltage reference. The non-inverting input is connected to the power supply output. So here is pin 5. Over here, that's the one that was connected to our reference. That was our set point. But now that's connected to our output. Pin 4, the inverter, is connected to this divider off of the sense output. And so this 7 volt, they have a divider here, and so this is right around 6 volts is what this pin 4 is being held at. So this is backwards from the way it was being used here. And this is just being used as a comparator, and this guy is going to go, he's just going to slam from rail to rail just based on which of these two is greater. If the positive input is greater, this is going to go to the positive rail. If the negative input is greater, this is going to go to the negative rail, which is 0 in this case, ground. Should something go haywire upstream, or this Darlington pair breaks down, we just get a short circuit across this, we start to get higher voltage on this output. What we want to do is, our choices are we either let that happen and we blow up every chip on the prompt board, or we clamp this output down and drag it down. We crowbar this down to as low a voltage as we can get, or at least a voltage that is safe enough for the board, and at the same time it's not such a low voltage that it's going to burn this drive transistor out. And that's what this does. As soon as this non-inverting input that is connected to the voltage output on pin 5, as soon as that goes above this set point, this output is going to swing to the positive rail. Okay, and this output is pin 9, which is the output that came out after that zener. Okay, so it's not the actual output, it's this zener. All that's going to do is that's going to drop 6 or 7 volts off of that output. So instead of this going all the way to the 12 volt rail, it's going to temper this a bit, and it's going to drop to something a little bit more modest, because this SCR, and I guess I should have said that earlier, what this is doing is it's going to fire this SCR right over here. This SCR only needs 1/4 of a volt to fire or so. We don't need all 12 volts on that, so they temper it with that zener, and then they've also got a voltage divider here to drop that down. So this will go above 1/4 of a volt. That'll turn this SCR on. This SCR will pull down this 5 volt output to as close to ground as it can. The current foldback was all calculated out so that this transistor can handle that indefinitely. It can stay forever in that current foldback. What happens then is we have to turn this power supply completely off. We have to remove any current, any bias across that SCR. That SCR will recover. Then we turn the power supply back on again, and this would go back to normal. But if something is wrong with this upstream, this Darlington, let's say it's shorted out, now our only choice is that this SCR is going to fire, and the only way it gets out of this is it has to blow a fuse somewhere upstream, or it has to burn something out. When you say crowbar, what you really mean is something that's going to trip something else and cause a fuse to blow. As I mentioned, unlike the current foldback, which we only have to go to we only have to draw a current that's below the short circuit current. With the SCR, we have to completely remove the power, because that's the only way that SCR can recover. And if you weren't expecting a crowbar to be in here as some kind of a protection, that's the effect that causes that little bit of sweat to form on your brow when suddenly this power supply just goes to 0, and you're really relieved when you turn it off and you turn it back on, and it just recovers as if nothing happened. Probably that's because there's this SCR inside. SCRs are nearly bulletproof. Overvoltage, overcurrent, or transients theoretically can cause an SCR to fail, but you would really have to work at it. If they do fail, most likely the failure is going to be a short between the terminals, so we would know that immediately, or maybe a degradation of the blocking voltage. But rarely will they ever fail open, which is fortunate, because if it failed open, we wouldn't know it. This is our fallback situation, and if it failed open, we wouldn't know it. So fortunately, they never fail, or they rarely fail open. Replacing this 723, it was just a mechanical process. You had to take off this, you had to undo these this is the SCR and the little voltage regulators over on that side. You had to take those off. Here's the main transistors, the big power transistors on the back. This is where the 6055 was. Had to desolder where those come through to this PC board, and then it was just mechanically, taking this apart. And while I had this apart, I was able to then pump the back of the 723, take that off. I also, while I had it apart, because these are dirt cheap, I replaced the main Darlington pair, and I didn't have a 6055, so I replaced that with a 6057, which is a little bit better transistor. So replace that, put it all back together. While I had it apart, I did a bench test on this 723, and yeah, it indeed did not have, I could make the reference voltage do whatever I wanted to do on that. Reassembled this, put it back under load the way it was before, tested it, and it's rock solid. There's absolutely no droop on this all the way up to the 8 amps. I get to the 8 amp knee, it rolls off very nicely, goes into current foldback, 3 amps, and I've run it at 3 amps for a long, long time, and nothing gets too hot. So it's absolutely happy doing that. There is another little problem, and that is that this thing has got, I think the drawings said that this is 40 inches long. So they've got 40-inch wires going from this connector to the connector that goes into the side of the prompt. At 3 amps, this has almost a quarter of a volt drop across it by itself. I wound up compensating for this by trimming up the power supply a little bit. So when this is plugged in, I'm on the proud side of 5 volts. On the board itself, it's just a little bit on the shy side of 5 volts. From all the testing that I've done so far, it seems to be working just fine. I've hooked up the serial port, I've uploaded programs, I've downloaded programs. So this all seems to be working just fine now. Okay, I know this was a bit much, but who knows? Maybe there was some interesting information or some useful information on LM723s. A very, very key chip in the advancement of power supplies, as I said, going back to the late 60s. It's a workhorse. For anybody that's working on vintage computers, they still are a workhorse. They're, you take a lot of power supplies apart and you'll find one of these guys inside. So I hope there was something here that was helpful for you the next time that you come across any slacker 723s that took early retirement and aren't doing their job. After I finish more documentation, I might take a few more waveforms of what a working board looks like, so I have those in case something happens to this again. I'll get it buttoned up and back on its place over there with the other development systems. If there's an interest, I can do a video on actually operating this and what you can do with a Prompt 48, and that's when you can really see its utility of the capabilities it gives you as a developer for this. All right, well that's it. Thanks for watching. I will talk with you later. Bye-bye.